Alright, so last time we talked about this computing a regression equation. We talked about computing B naught and B1 given our sample data was the key thing. So I wanted to represent how this would look in an actual situation. So let's go back to this this classic example of we go out and randomly select people's height and we ask them their height and their weight, and we plot their height on the x-axis and their weight on the y-axis. And we notice this general trend, and we suppose that the relationship between x and y is indeed linear, and we estimate the parameters beta naught, the intercept, with the random variable b naught, right, and b1. And given our sample data, this is what we get. B naught again is this little distance here, and b1 is the slope of this line. So what I want to do today is first just introduce the idea of the residual and just the general idea of an outlier. So first of all, you'll notice when you look at this, hopefully you'll notice immediately that this observation here is outlying. It's not in line, that is, it's not in line with this general trend that we see. You know, in general we see that taller people tend to be heavier, and but you see this observation actually probably better depicts this. This person is very tall, say 75 inches, but not very heavy. I just made this data up. I don't know if anyone's this skinny, but so you'll notice that these two observations are outlying as in with respect to this general trend that we see. That is, they're far away from what we really predict them to be. So how do we express this distance? This is, let's say this is the ith observation. The ith residual is defined this way: EI equals YI minus YI hat. That is what this person actually weighs and minus what our regression equation would predict that they would weigh. So this minus this. This is the observed data, observed minus fitted. Similarly for this person. So let's say this is the jth person that we sample. It could be the third, first, whatever. This one, notice especially that this person has similar, there are lots of other data points with a similar weight, right, around 90 pounds or 100 pounds, and there's lots of similar people in this data with similar height, say 75 inches, 72 inches, right around here. But this observation is outlined with the general trend. Now notice this observation here, it's outlying with respect to its x values and y values, but not with respect to this general trend. That is, say it really falls in line with our regression equation, but this person's height and weight are really this person's height and weight are really far out from where most of the data is. Most of the samples' height and weight is recorded. So what I wanted to show today is really that there's three types of variation here. Imagine that we go out and we do this and we compute the sample's mean weight. So that's going to be a mean weight. Say it's right here. That's probably a little lower than that, but let's say right here. Doesn't really matter, but y bar. So that's just the sum of all these people's weight divided by the number of people that we took in our sample. So you'll notice three types of variation. You'll notice we've already talked about how far each person outlies, or the distance, the ith residual of each person is their observed value minus the fitted value, and but also there's the distance of how far they are from their mean. So let's say this person has this distance, right, from the mean, um, from the mean weight, that is. And there is, we also want to express, there is the distance between how far our regression equation is from the mean weight. So let's say at this observation here, this observation. So these are three quantities that I really want to stress today. So number one, we call this is the sum of squares of error, which is the sum of the EI squares. So SSE. SSE, sum of squares of error, which is the sum from I equals 1 to n of yi minus yi hat squared, which is oh, I don't really need that equal sign here. This is This is what we call the SSE, and similarly, I want to introduce to you the SSR, or the sum of squares due to regression. So this is the sum of yi minus, sorry, the sum of yi hat minus y bar. This is how far each data point lies from the regression how far the fitted value lies from the sample mean. So, and this is also squared. And the other one is the last one, which is the sum of squares of total error, which is the sum of yi minus y bar squared, SSTO. Now, there are two important relationships. Actually, this is one I wanted to stress here. Notice this is the observed minus the fitted squared, so this is equal to the sum for SSE, sum of EI squared. Alright, so let's make this a little bigger here. Let's talk a little bit more about this. Alright. So you'll notice the SSE and SSTO and SSR, they all have one thing in common. They have this square for each of these terms. And I want you to note this is because we need to counteract, well, counteract, I shouldn't say counteract is a bad choice of words, but we want to count equivalently people that are far outlying below the regression equation and far outlying above equivalently. So, and that's one way to do that is to take the square. So, anyways, there's two relationships I really want to stress, and number one is this: SSTO, sum of squares of total error, is equal to SSR plus SSE. And the other one I wanted to stress is, and we'll see why this is important. So this is one that I wanted to stress, but the other one that I wanted to stress is the sum of part of the reason why we need this squared. The sum of EI is equal to 0. This is an important relationship. And we'll see why this is so important. But for now, let's try to show that. So the sum of EI is equal to 0. So this is equal to, how do we show this? Sum of EI is equal to sum, just using the definition, yi minus yi hat. We know what yi hat is, so sum of yi minus, sorry, yi hat is b naught plus b1 x bar, I'm sorry, xi, b1 xi. And we know what b naught is. We have that formula for it, so let's use that. So let's go ahead and say this is equal to the sum of yi minus b naught is equal to, again, it's y bar, and the sum is all still outside here. So y bar minus b1 x bar plus, oh sorry, if we distribute this negative, we don't have plus, we have minus b1 x bar. But this was b naught, so this sign becomes a plus, because remember b1, remember this relationship, this is b1 is equal to y bar minus b1 x bar. So we have plus there, and right away you can see that this cancels with that. So, and if I take the sum, if I bring the sum inside, I have this is equal to the sum of yi minus the sum of y bar, and this is from I equals 1 to n, so I have, and let's rewrite this in terms of y bar. This is just, we can rewrite this as n y bar, and similarly there's n observations, there's no I here, so we can rewrite this as n y bar, and this is equal to 0. Alright.